Good evening, dear Professor. I would like to submit my homework to sharp number 2 about explain the PID controller and an example for neural plant. PID stands for Proportional Integral Differential Control System. P stands for proportional. I stands for integral, and D stands for differential. PID controller are a type of feedback control system that use feedback to control a process or system. They are widely used in industrial applications such as manufacturing, robotics, and process control. The PID controller is responsible for ensuring that the process remains as close to the designed value as possible, regardless of value disruptions. The PID controller determines how much and how quickly correction is applied by using varying amounts of P and A and D action. The proportional block creates an output similar to proportional to the magnitude of the arrow singular. The integral block creates an output proportional to the duration and magnitude to the arrow single. The derivative block creates an output single proportional to the rate of change of the arrow single. If there have a control system that can make the set ports completely and correctly passed to the control objects, then we do not need PID control. The truth is that it's impossible. First, let's refer to the difference between the process variable and the set port as the arrow single. If the controller can't make the set ports complete and correctly passed to the control objects, there have some arrow singles. It can be need PID to continuously adjusting the control input. By combining proprietary interior and derivative actions, it aims to reduce the error and stabilize the system, ensuring that the process variable closely follows the setpoint with minimal overshoot and oscillation. Next is the expression of proportion. The proportional response can be obtained by multiplying the error by the constant Kp, also known as the proportional gain. Because the high proportional gain, the error value can also vary greatly. But if it's too high, the system becomes unstable. On the contrary, the result control system with no proportional gain will be less responsive to the process. Like this, it's the expansion of integral. The result of the integral term, sometimes called a reset, is proportional to the size of the arrow and the duration of the arrow. Sum of arrows over all time period. Arrow interval gives what should have been the cumula- cum- cumulative offset cumulative arrow times the intergame. The size of the effect of the integral term is determined by the integral expansion rate. The integral term, when used in combination with the proportional term, accelerate the process to the desired point and emin- e- and elimini- eliminates the residual error caused by owning the proprietary term. However, however, the integral term the integral term is response to past cumulative errors. Therefore, it might be need to overshoot. Next is it's the expression of derivative. The- It's the expression of derivative. The rate of change of the process error is calculated by taking the slope of each error and multiplying it by the derivative gain. The influence of KD derivative term depends on the derivative gain rate. The derivative term slows down the rate of change of the output signal of the control system, thereby helping the control system reach the desired point. Therefore, the differential term is used to reduce the overshoot amplitude caused by the integral term and improve the stability of the control system combination. Next, I will explain the PID how to works. The proportional block creates an output signal is proportional to the magnitude of the arrow signal. Unfortunately, the closer you get to the setpoint, the less it passes. Lastly, the process just runs continuously close to the setpoint, but not quite here. That That's when integral jumps in. The integral block creates an output proportional to the duration and magnitude of the arrow signal. The longer is the longer the arrow and the greater the amount, the larger the integral output. As long as an arrow excites, integral action will continue. The derivative the derivative block creates an output signal proportional to the rate of change of the arrow signal. The faster the arrow changes, the larger der- the, the, de- the derivative output. Deri- Derivative control looks ahead to see what the arrow will be in the future and contributes to the controller output accordingly. So the PID controller used three components to calculate the control output: proportional, integral, and derivative. Each of these components work together to adjust the control output to reach the desired setpoint. In this paper, I will explain the meaning of the setpoint, overshoot, undershoot, reset time, settling time. Setpoint means the desired target value that the PID controller aims to maintain. Overshoot means occurs when the process variable exceeds the setpoint before settling down. It's an indication that the system is too aggressive or have too high a populational gain. Under Undershoot means when the process variable drops below the setpoint before scrutining itself. This typically happens if the system response is too slow or the control actions are too mild. Raise time means the time taken for the process variable to go from a central percentage of the endpoint to another percentage of the endpoint. It indicates how quickly the system responds to change. Settling time means the time it takes for the process variable to remain within a central percentage of the endpoint without significant oscillations. It shows how quickly the system stabilized around the setpoint. For this example, the example is among small ones in translation under the action of a spring and a cyanide. Like this, the equation of the system is this. The Laplace transform is this, and the Fs and the Xs relation is this, equal to 1 over m plus s to the second power plus bs and plus k. This let set m equal to b equal to 15 and k equal to 30 and f equal 1. We put this data into the expression so we can get this expression. The T is equal to 1 over 2 s to the second power plus 15 s and plus 30. For this expression, We use MATLAB to calculate. Input num equal to 1, then equal to 15 and 30. Define T equal to TF num and design. Correct step T. We can get a graph of the figure like this. As we can see, the curve is not smooth. The curve is not smooth. So we can set the Kp equal to 300. And the expression became this. And we can get the detail of this one, of this, and plus the Kp equal to 300. We can get the last expression equal to 300 over 2s to the second power plus 15s and plus 330. We can use MATLAB to calculate. Input num equaled 300, then equal to 2, 15 and 330. Define T equal to TF num and dim. Connect the step T. We can get a graph of the figure like this, right in the right. We can see that the curve is relatively stable, and we can set the Kp equal to 300 and the Kd equal to 10. The expression becomes like this. We can get the expression is this equal to 10s plus 300 over 2s to the second power plus 25s and plus 330. We can use MATLAB to connect. Input this num equal to 10 and 300, then equal to 2, 25, 330. Define T equal to TF num and then connect the step T. We can get a pro graph of the figure like this. We can see that the curve is relatively stable. In the last, like this, we can change the Kp equal to 30 and the Ka equal to 30, equal to 17. The Ka is new input. The expression becomes this, and put this data into the expression and equal to this. We can use MATLAB to calculate. Input num equal to 30 and 70. Then equal to 2, 15, 60 and 70. Define T equal to TF num and dim. Connect the step T. We can get a paragraph of the figure like this. We can say that the curve is relatively stable more than. In the next, we can set the Kp equal to 350, Ki equal to 300, and Kd equal to 50. The expression becomes this. The next expression. We get this data into the expression and got the expression like this. And use MATLAB to connect. Input the num equal to 50, 350, and 300. Then equal to 65, 380, 300. Define T equal to TF num and then. Connect the step T. Got the next graph of the finger. We can see that the curve is more stable. The result is what we want. So the result is Kp, Ki, and Kd. That PID controller together work. So this result is we want the next result. Okay, this is my introduction of homework 2 sharp. Number 2 about explain the PID controller and an example for linear plant. Thank you, sir.